Hey everybody, Mr. Bowman here. This video is another one on 3.14 probability distributions, and this time around we're focusing on the 6 merit questions from the 2021 exam. Just a reminder, all of these questions were actual past questions from actual exams. I've just kind of compiled them together on the Quick Maths website to make your life easier. So do check out the link in the description to this video if you want to see a bank of more questions. So let's get into question number 8. So it is estimated that on Memorial Drive in Christchurch, the probability of 0.45 of being required to stop. So I'm assuming that means the 0.55 is not being required to stop. And there's six traffic lights in total. Distances range between this number and this number. That's all good. Suppose that the number of times a driver is required to stop at the 6 sets of traffic lights when they drive the complete length of Memorial Avenue can be modeled by a binomial distribution. That's lovely to see because it takes the guesswork out of what distribution to use. Justify the use of a binomial distribution model to calculate the number of times they're required to stop when they complete the length of Memorial Avenue. So basically, why is a binomial distribution appropriate here? I is going to be quite wordy, so let's start I by kind of typing up our response. So I guess the conditions or assumptions of a binomial distribution are what they're trying to draw on us to talk about. So just a reminder, those are fixed number of trials. So hopefully you've got these memorized in your brain. Fixed number of trials, 2 possible outcomes was the next one. They have to be kind of random, don't they? So they've got to be random. And then finally, they have to be independent from each other. But I should note that randomness relates to the, having a constant probability of, in our case, 0.45. So you can't have different probabilities and different outcomes is what it's saying. So let's think about, do we think it's appropriate? So is there a fixed number of trials here is the first thing. And in this case, there are 6 traffic lights. So each of the traffic lights will be a number, one of the trials. So so in this case, that one looks good. There would be a fixed number of 6 trials, each representing, gotta type it there, 6 trials, each representing one of the traffic lights along Memorial Drive. I haven't got the capital letter there. So that one there kind of checks out, doesn't it? So 2 possible outcomes. So again, this one checks out. You're either required to stop or not required to stop. So we're pretty happy with this one again. So there are only 2 possible outcomes for each of the traffic lights, being that they are required to stop, which is the red/amber traffic lights, or not required to stop, being the green ones, which lets them carry on through. So that one checks out. And this is where I had an issue with the particular use of a binomial distribution. So I think these two here are kind of actually interrelated to each other the more I thought about it. So let's kind of put them in the same discussion. And so for me, when I'm driving down the traffic lights, I always think of Wairoa Road on the North Shore where I'm from. I assume it's going to be similar to Memorial Ave. So it does seem like the traffic lights along this big main road, they are kind of sequenced to each other. They are literally programmed to kind of let the traffic flow through that. So for me, I don't think it's going to be random. And I don't think they're going to be independent of each other. I literally think there's going to be a computer program which has sequenced these lights to kind of allow traffic to flow. Imagine 6 traffic lights. Imagine if they were random, it would be traffic chaos. And I suspect you wouldn't be able to get anywhere around Christchurch anytime soon. So I want to talk about that for this case here. So the things I've said, so where the use of a binomial distribution may fall short is that the probability of success, i.e. 45% chance of being required to stop at each traffic light, and the independence of each traffic light. So that's where I think they fall short. I don't think this one works. So I suggest that to aid the flow of traffic down Memorial Avenue, and that's what I talked about before, Memorial Avenue, the 6 traffic lights would be programmed in sequence to ensure traffic flows appropriately. So that's what I'm talking about. So I've gone the point of the first half of this paragraph. I've said, I think the use of a binomial distribution is going to fall short. I've then said, in the real world, what I think actually is going to happen. And I think the programming in sequence is probably going to mean that it's not random. So I now want to link it back to the issue I have. As a result, I don't think the traffic lights are going to be independent of each other, and I don't think we're going to have that constant probability of success. I think that success will change based on when you enter the traffic light sequence. So, as a result, I doubt the traffic lights would be independent of each other, and I also doubt that there would not be a constant probability of getting through the traffic lights. Rather, it might depend on what time relative to the sequence the vehicle entered Memorial Avenue. There you go. Was it Memorial Drive or Memorial Avenue? Okay, I think I might have wrote Avenue somewhere. Avenue. There we go. So just noting, gosh, I've had some typos here. That's meant to be Avenue as well. And I definitely spelled that wrong as well. Anyway, let's ignore those for now. So there should be a D dash in there. So I doubt. So for me, that wraps up I pretty well. So I've basically said a normal distribution model, not appropriate for here. The model answers to this, if you check the NCQA schedule, they've actually got the opposite response. They did think these ones are fine. But I do want to note they were happy to discuss or accept either combination of answers. Okay, so we're now into the calculation part of this. So you did need a combination of these to get the merit mark. So I down here. So estimate the probability that a driver is not required to stop at any of the lights or is required to stop at all 6 lights. So this one here was a bit weird. So firstly, I basically just said don't use a binomial distribution, but I'm going to go ahead and use it. So just to help my response, so I've just said assuming that a binomial distribution is appropriate. And then, as I said, we know for sure that it's not, or may not be anyway, is appropriate. And then I'm going to start doing my calculations after this here. So I guess it's been basically asked us, so we're trying to find the probability of not stopping or stopping at all of them, right? Probability of not stopping or stopping at all. And this time around, so basically that's going to be the probability of x being equal to 0. So that's stopping at 0 traffic lights. And we're just going to add on the probability that x is equal to 6. So that's being required to stop at all 6 traffic lights. You're going to go into your binomial distribution calculator. So you're going to go into binomial point distribution mode. So BPD. Don't use BCD for this mode because you'll get the wrong answer. If you're not sure what all this means, let me know and I can reply with some helpful resources. When I did that, when I put x is equal to 0, that got me to 0.0277. And I added on the probability that x was equal to 6, and that there was 0.0083. And when I got that all together, that got me to 0.0360. That there had a 4dp rounding. So roughly 3 or 4% chance of catching all the lights or missing all the lights if a binomial distribution was relevant. Okay, so we are now on to question number 9. So we've got wilding pine trees, hopefully I'm saying that right, are a serious threat to natural landscapes. Blah, 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 basically there's stuff that's not deliberately planted, blah, 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 shows that on dealing with Rangitoto Island, the average number of wilding pine trees is 1.8. So because we're dealing with an average, we've got the word per hectare here. So that really is giving a huge giveaway of something to do with a percent distribution. Conservationist considers it a success when the probability of finding at least one wilding pine tree in a hectare is 1/3. So that means the probability of there being at least one, so that's that one there, is equal to 1/3. Calculate the model parameter that provides this result. So key word to note is they haven't given us the parameter. So that's what we're trying to find out. So even though we're given this average here, they're basically trying to say, well, that average isn't relevant. What average do we need to meet this criteria here? So it looks like in this case, we're dealing with an inverse percent distribution question. So it's going to be inverse percent distribution. And it's asking us to calculate a lambda that would be relevant to the 1/3 probability that we've got. So as I said, the probability that there being at least one of these trees, it's a success when that happens 1/3 of the time. So that means the probability or the desired probability of there being 0 of these wilding pine trees in a particular thing is going to be 1 minus that probability. So that means, a success occurs when 2/3 of the hectares on Rangitoto Island don't have any of these wilding pine trees in them. So because it's an inverse percent distribution question, so the probability that x is equal to 0 is always equal to e to the power of negative lambda. And we've just calculated what the probability that x is equal to 0. So I'm just going to sub that in down here. So that means 2/3 is going to be equal to e to the power of negative lambda. And this here is just an algebraic equation because e is actually a number. So I'm going to plug this into the solver function of my graphics calculator. If you don't know how to do that, let me know and I'll reply with a relevant video. And when I plugged that into my graphics calculator, I got an average of 4.6, and that there had a 1 dp rounding. So what this means is, so we had an average of 1.2, but so it means if we had an average of 4.6 or less, that means we're going to get, this 1/3 probability that they're talking about here. So because this is a merit question, I've got the answer, and this is very mathy. I now just need to explain what that number actually means in context. So this means, a parameter of lambda equals 4.6, and that basically is the mean number of wilding pine trees per hectare, isn't it? Per hectare would result in a success, and a success being finding at least one wilding pine tree in a hectare to be 1/3. So finding a probability of at least one wilding pine tree in a hectare to be 1/3. So that wraps up that question. Just a reminder, it is really important to explain your answer in context, particularly if it's a merit question and there's no context. You need that there for your mark. Now on to question number 10. And for me, I thought once you broke down this question, so once you read through it, this is actually the easiest merit question in this exam. So we've got two different computer operating systems. We've got system A, system W. You can kind of see them down here in that table. And basically, it just says compare the probabilities of buying 5 or more extras when you get system A versus system W. So what this table means is if you buy system A, the probability of getting 0 extras was this number. And then if you got system W, the probability of buying 0 extras was this number here. So we're dealing with 5 or more, so we're dealing with this slot over here. So the first thing I want to calculate is, for both systems, I want to calculate the probability that they got 5 or more purchases with their acquisition of the two systems. So let's deal with system A first. So we've got system A, the probability that X is equal to or greater than 5 is going to be equal to these two, or these three here added together. So it's going to be 0.08 plus 0.04, and then we're going to add on the 0.02. And adding that all together, so that's 0.14, or roughly 14%. Let's do the same with system W now. So system W, the probability that they bought 5 or more accessories with the purchase is 18, 14, and 15 all added together. So it's going to be 0.18 plus 0.14 plus 0.15. And when I add that together, I get 0.5 or 0.47. So I think that's where you kind of got the achieved mark. And now it's asking us to compare them. So I always compare stuff through relative risk. So for me, that's a comparison. So my relative risk is always equal to my bigger probability divided by my smaller one. So I'm going to do 0.47 divided by 0.15 or 14. And that gets me to 3.36, and that there had a 2 dp rounding. So that relative risk number is going to be the basis, or hit my microphone then, that's going to be the basis of my calculation, or my comparison rather. So basically this tells us that people who purchase system W are 3.36 times more likely to get 5 or more extra accessories than compared with people who purchase system A. So we now need to explain that in a sentence. So this means people who buy system W are 3.36 times more likely to buy 5 or more extras with system 5 or more extras than those who purchase system A. And that wraps up this question. Okay, so we're now on to question number 11 for both system types. So this is kind of carrying on with the system W, system E, so system A, system W for the previous question. It is believed that the time taken for a serious system issue to occur can be modeled by a normal distribution. Again, that's really nice to see, so I don't have to do a guess and check about what distributions it is. We've got a mean of 5.5 years and a standard deviation of 0.9 years. So that's trying to say, on average, that your system is going to have a serious issue within about 5.5 years. And we've got that variation of measure there as well. So estimate the probability that, so we've got the word given, so this is going to be a conditional question, that a computer that lasted for more than 6 years until its first issue will also last more than 5 years. So basically what we're going to do is we're going to start off by finding the probability that X is greater than 6. So that means it took more than 6 years to have this serious issue. Following that, we're then going to find the probability that X is greater than 7.5. So that relates to the last part of it. And then once I've got that, I'll show you how the conditional part of the question is going to help out. So let's do the 6th one first. So there's my graph. So I had a mean. The mean was 5.5. I'm ignoring that pen error again. So 5.5, and we had a standard deviation of 0.9. And we're trying to find 6 or greater than 6. So that's going to be this chunk here, right? So when you put that in your graphics calculator, using the NCD mode, if you don't know how to use that, let me know. Your lower is going to be equal to 6. Your upper, and this is a bit of a trick, your upper is going to be equal to lots of 9. So shove in a really big number there. So that represents the upper limit up there. Your mean is 5.5, and your standard deviation, and that there was 0.9. So you plug that into your calculator. When I did that earlier, so I got the probability of being greater than 6 to be equal to 0.2893. Hopefully you're getting the same as me. I'm now going to repeat this process to find the probability of it being greater than 7.5. So we've got our new curve. It's going to be the same data. It's going to have a mean of 5.5. the standard deviation is still 0.9, but this time around we're dealing with the top, we're dealing with 7.5 or more. So same again, we're using NCD on my calculator. My lower is going to be equal to 7.5, and my upper, mean, and standard deviation are all going to be the exact same. So they're going to be the same as my previous question. And when I put that in my graphics calculator, so the probability that the time to get a serious computer issue being more than 7.5 years, I got 0.0131, and that there had a 4 dp rounding as well. So I've done the hard work, and now I'm going to just wrap it up. So I'm trying to find the probability that the computer issue went beyond 7.5 years given it lasted more than 6 years. So if you think of your F over T, so T stands for the total outcomes, the outcomes that we care about. And because the question said the word given, we only care about the computers that had the serious issue thing after 6 years. So that was the 0.2893 that we calculated earlier. And of this 0.2893, 0.0131 of them went beyond that 7.5 year window. So that's my conditional part. That was what made this question quite tricky. And then when you put that fraction in your calculator as division, you're going to get 0.0453, and that there had a 4 dp. So that's trying to say if your computer lasted for more than 6 years to get to have this computer issue, there's about a 4 or 5% chance that you'll actually get all the way to 7.5 years without having that. So we're up to the final merit question from this video. It turns out there's actually 5, and this question carries on with this computer-related stuff that they've talked about. And we've now got a third computer system known as computer system L, so system L, and it is known to experience serious issues within the first 2.5 years or more than 8.5 years. So either basically your computer has an issue really early or really late. So those two computer issues, or actually not that much, so it's only 4% of the time it's going to be really early or really late. So most of the time, the other 96%, it's going to be somewhere in between the 2.5 and the 8.5. So justify whether the parameters mentioned in the previous question, so the parameters mean refers to the average and the standard deviation, can be used to model the system error for L. So this one here, it does sound quite tricky, but all you've really got to do is using the parameters above here, you're trying to find, so for system L, we know that the probability that x is less than 2.5 plus the probability that x is greater than 8.5, we know that's going to be equal to 0.04. So using the previous parameters, we're going to calculate the probabilities here. We're going to add them together, and we're going to check if it's roughly the same or if it's really, really different. So I guess let's get into it. So let's start off by doing the probability that x is less than 2.5. So I've got my normal distribution curve, and my mean is 5.5. My standard deviation is 0.9. And I'm trying to find less than 2.5. So that kind of relates to this area here. So again, I'm using my NCD mode. My lower is negative a whole bunch of 9s because I'm dealing with that left tail. My upper is the 2.5. My standard deviation is 0.9. And then my mean is equal to 5.5. So when I put that all in my calculator, I get the probability that x is being less than 2.5. All of that for me was 0.0004, and that there had a probability rounded to 4 decimal points. So I've got that sorted. So that's that part of the question. I'm now going to repeat the same for this part of the question. So I now need to find the probability that x was greater than 8.5. So again, sketching my graph. So there's my poorly drawn graph. That's a mean of 5.5, standard deviation of 0.9. And we're trying to find this shaded area of 8.5 or more. So again, NCD mode, so huge normal distribution questions in this one, but that's positive lots of 9s here. We had our upper of, oh no, gosh, I got my lower wrong. Actually, my lower is the 8.5, isn't it? 8.5. And my upper, being that right tail, was the 5 9s, or 6 9s, however many you teacher told you to put. My standard deviation was 0.9, and my mean, again, 5.5. So I got the probability with my graphics calculator, so x being greater than 8.5, had the sign the wrong way around. I got that to be also 0.0004, and that they had a 4 dp rounding. So when you add this and this together, that's actually 0.0008, which isn't even close to 0.4. So we know that 0.0004 plus 0.0004 does not equal to 0.04. It's actually quite different. So that there is actually 0.04% compared with 4%. So that tells you, because you got the dissimilar, that tells you the system L data we've got here does not match the parameters or the data we've got there. So we now need to explain that in a sentence just to state that those parameters are not relevant for system L. I'm just going to type up my response here. So the 0.08, I just realized my calculation down the bottom there was wrong. That should be 0.08 percent. Well, where's my percent sign? There it is. 8%. Calculated using the parameters or parameters of the normal distribution model for the other systems is much less than the stated 4% for system L. This suggests that the parameters used for system A and system W would not be appropriate for system L. So you're going to somehow need to find out that data, the mean and the standard deviation for system L. So that wraps up all the merit questions from this video. I felt a bit rushed in the video, so hopefully it all made sense. Keep an eye out for the excellence questions and the remainder of the merit ones coming up soon. And then, yeah, if you do need any questions or any extra resources in relation to the stuff chatted about in this video, honestly, don't hesitate in getting in touch. More than happy to help out.